Swayam Prabha. Digital India. Educated India.
Now we will see some proof templates for various common kinds of statements or propositions. So remember, this was our picture of what a proof looks like. You start with some propositions that are already proven or are the axioms and definitions in the system, and you make deductions at each step using any of the previously available propositions to get an implication to the next proposition in the sequence until you hit the last proposition, which is what you wanted to prove. Okay. So now that's the basic template, but depending on the kind of statement you want to prove, you can do a few extra things. So that's what we're going to see today. So let's see how you prove a statement of the form P implies Q for some propositions P and Q. So here is what a typical proof for that would look like. You would start off by saying, suppose P. You're going to put this P as your P0. Now this is a little tricky because I said we should start off with a set of propositions that are known to be true, and in this case P is not known to be true. So technically you're not allowed to start off with P in that list. Okay? But we'll still do that, and the plan is we'll suppose P, we'll assume P, and then proceed using normal steps of deduction until you manage to prove Q. So why is this a valid proof of P implies Q? There are a couple of ways to look at it. So here's what you could think of as happening. So if P is true, then this was a valid proof. It was okay for us to put P as our starting point in the sequence of propositions because it is a true proposition. And then we went ahead and proved Q. So actually this is a valid proof of Q. Okay, and if Q holds, then P implies Q holds. So that would be the kind of lucky case. But what if P is false? Then what we just now did is not at all a valid proof. But in this case, we are covered because P is false, and therefore P implies Q is vacuously true. So in either case, we have P implies Q. In either case, P implies Q is true, either because we have written down a valid proof of P implies Q, in fact a valid proof of Q, or because P implies Q is vacuously true. Okay, so this is how a proof of P implies Q would look like. Now if you feel a little uneasy, that this is not quite sticking to what we set down as the framework for proofs, well, then you can actually rephrase this as a proof which is sticking to that framework. So the first statement here is not P, but P implies P1. So in your original proof, if you had P0 equal to P as a first statement, and then P1, P2, and so forth until you hit Q, in the new proof, you would start off with P implies P1. Okay, and this would be a true statement, which is what allowed you to go from P0 to P1 in the original case. Right? So you start off with a true statement, P implies P1. So you're not creating any, not stepping out of this framework of the proof from that I mentioned previously. And then the next step, you're not proving P2, you're again proving P implies P2. So each of the steps, the original deductions, they were P1, P2, and so forth. Now they're all P implies P1, P implies P2, all the way to the last proposition. Instead of being Q, you will get P implies Q. Okay? And you should convince yourself that if the original proof, starting with P0 as P, was a valid sequence of derivations, then so would this be. So this would be a valid way to rewrite a proof, using what I just now said, starting with suppose P. If you take a proof of that form, you can rewrite into a proof which doesn't make any such supposition, for which you don't need to go through this kind of a mental exercise to convince yourself that it is a good proof. Okay. However, this is a little cumbersome to have this P implies in every proposition you're stating along the way. So the standard practice, what would be more readable, would be to put suppose P as a first statement and pretend that P is true. It's available to you as a true proposition to work with, and keep deriving everything else. It's exactly equivalent to having this sequence of propositions in your proof. It's just a little less cumbersome to stick to. Okay. All right. So that's what you should do if you are asked to prove P implies Q. You can start off by supposing P. Very useful way of doing proofs often is not to start with the statement you're supposed to prove directly, but to rephrase it into an equivalent proposition, and then prove this equivalent proposition. Okay. Again, doing that is, so this is what it look like, right? You start off with the original proposition you're supposed to prove, you write down an equivalent proposition, which I'm calling P equivalent. And then, so, that equivalence should be evident. It should come from propositional calculus, something basic, and you state that equivalent statement and then go ahead and prove that equivalent statement instead of the original statement. And again, this is not really stepping outside the framework. If you wanted, you could have just forgotten that first declaration you did here and just gone ahead and taken the proof all the way to the equivalent statement, and then did one more derivation to get the original statement. Indeed, if P equivalent implies P original, then you can add that as the last step. Okay, so that would have been totally fine. What is the point of stating this equivalent statement up front? This is to guide yourself and the reader as to what is going to happen in this proof, so that you know where the next step is taking you. It will take you all the way to this equivalent but different formulation of the original proposition. Okay, and if you're doing this, it's important to state what this equivalent proposition you're trying to prove is, because depending on that, subsequent steps in the proof could look a little different. Okay. And here is a very important example of using a rephrasing, and that's to use a contrapositive to prove an implication. So suppose you're originally asked to prove P implies Q, you would first rewrite it as not Q implies not P, and then you would go ahead and prove this statement. And if you notice here, it's important to, and now this proof would start off by saying suppose not Q, right? So when somebody asks you to prove P implies Q, and if your proof starts off by saying suppose not Q, that could be confusing. So that's why you would say, first, instead of proving P implies Q, I will prove not Q implies not P. For that, suppose not Q. Okay, so that's important to state the equivalent statement upfront, make it clear what it is, and then proceed with the proof of the equivalent statement. Okay. And this equivalence, by the way, is something we have already seen. This is just saying both of these expressions or formulas. As formulas, they are just saying not P or Q, okay, for any variables P and Q. So this you have seen, so that's why it's legitimate to start with the contrapositive instead of the original implication. So let's see a quick example. So as to why this is useful, here is a proposition which says that for all positive integers x and y, if x times y is strictly greater than 25, then either x is greater than or equal to 6 or y is greater than or equal to 6. Okay, so how do you go ahead proving this? In principle, you're supposed to look at every possible pair of integers which multiply to something greater than 25. So maybe you could go over the numbers 26, 27 and so forth, and look at all the ways in which it could come as product of two numbers. So 26 could be either 26 times 1 or 13 times 2, and in either case one of the numbers is greater than or equal to 6. Then you move on to 27, you'll say, okay, it's 3 times 9 or 27 times 1, and in either case that 9 or that 27 is greater than or equal to 1 and so forth. But this is not going to be a good idea for a proof because there are infinitely many numbers and you're never going to enumerate over all of them. But let's think about how you prove the contrapositive. To prove the contrapositive states that for every xy, if negation of this right hand side holds, so if not x greater than or equal to 6 or y greater than or equal to 6, and that is to say x less than or equal to 6 and y less than or equal to 6, then the negation of this holds. That is to say their product is less than or equal to 25. And so that's the statement you need to prove now. For every xy, if both x and y are strictly less than 6, which means they are each less than or equal to 5, then their product is at most 25. And that's much easier to see. There are only finitely many numbers to enumerate here. Or even better, you can argue that for positive numbers, the maximum of this x times y will be achieved when you allow x and y each to achieve its maximum allowed, which happens to be 5 each. So that's why the product can be plus 25. Okay, so once you rewrite it as the contrapositive, it becomes much clearer how you would do the proof. Here's another example that shows up in kind of higher level applications. So in cryptography, for instance, you build a cryptographic scheme based, and it's supposed to be secure based on computational hardness of certain other tasks, like say factorization of product of two large prime numbers, or there are other problems that that can be used to build secure cryptographic schemes. Now, what does it mean for a function to be hard? It means there are no efficient algorithms that compute that function. What does it mean for a cryptographic scheme to be secure? There are, of course, many details I am not getting to, but roughly it says there is no efficient algorithm that breaks the scheme for some sense of breaking the scheme. Okay, so you're asked to prove that if there is no efficient function for f, the efficient algorithm for f, then there is no efficient algorithm for breaking my scheme S. So how do you even give such a proof, saying that if there is no efficient algorithm for one task, there is no efficient algorithm for another task? That looks like you don't know how to get started. But suppose you look at the contrapositive of this. It's saying if there is an efficient algorithm to break my scheme, so if my scheme is not secured, so if there is an efficient attack on my scheme, then there is an efficient algorithm for this function f. F is not hard. Okay, so these are equivalent statements. But the second statement gives you an idea of how you might be able to prove this. It says, okay, somebody gave you an algorithm, an attack on the scheme, an efficient algorithm. Now maybe you could use that algorithm to build another algorithm. You can use that as a subroutine, for instance, right? So the proof can now be to show how to transform an algorithm that is attacking the scheme into an efficient algorithm for computing the function f, and that is often something you will be able to do if your construction is good. So this is how security is proven for all the cryptographic schemes out there, how security is based on the computational hardness of various problems. Okay, here's another example of rephrasing, which you may have come across, and that is proof by contradiction. So why is proof by contradiction rephrasing, or what do I mean by proof by contradiction here? So you're supposed to prove some statement P. Here is an equivalent statement you can rephrase it as, and that equivalent statement is not P implies false. So if you open up this expression in terms of or and not, so not P implies false is not P or false. So something or false is just something. So you're left with not P, which is P. Okay? So this is equivalent. These two statements are equivalent. So instead of proving P, you might as well just prove that not P implies false. Okay, but why is that interesting? Why would that make life any easier? So recall, to prove P implies Q, or in this case, not P implies false, you can start off by picking that left-hand side proposition and pretending that it is true. You can start off by saying, suppose not P in this case, right? So, in fact, there is a more idiomatic way of starting a proof by contradiction. You would say, suppose for the sake of contradiction not P. Instead of saying, we shall prove not P implies false, and for that, suppose not P, you just combine that into saying, suppose for the sake of contradiction not P. It's the same thing. At the end of it, you have supposed not P, and now your goal is to go ahead and prove false. Okay, so that's the last statement you're aiming to get to in your sequence of propositions in your proof. So your proof might look like something like this, not P, and then you derive some bunch of propositions. Along the way you got some proposition Q, you kept going, and you got another proposition not Q, and once you have this Q and not Q, they together yield false, right? Q and not Q implies false. Q and not Q itself is evaluates to false, and false implies false. So you can, so you would again maybe not write out this final thing as implies, that you derive the false, you derive false as your last proposition. Instead, you would stop here and say, okay, I got Q and not Q, and this is a contradiction. Cannot be the case that both Q and not Q together hold, hence P holds. So this is what a proof by contradiction often looks like. You start off by saying, suppose for the sake of contradiction not P, then you make a bunch of derivations and you get some contradiction like Q and not Q, and then you say, okay, I got a contradiction, hence what I started off here supposing for the sake of contradiction should be false. So you would say hence P holds. Okay, so that entire sequence of argument is just proving not P implies false, and therefore the equivalent statement P holds. Here is an example of proof by contradiction, which you pretty much cannot prove in any other reasonable way. Here is the claim. It's related to something called, it's related to a paradox, though here there is no paradox in this case. So here's a claim. There's a village barber who gives haircuts to exactly those in the village who don't cut their own hair. Okay, so if you are in the village, you get a haircut from this barber if and only if you don't cut your own hair. And the proposition I'm going to prove is that this particular claim, this proposition above, is false. So let's try to see what the actual formal statement of this proposition looks like. So I'm saying negation of the claim, right? So claim is what's here inside the brackets. It says there exists a barber in this village such that for everyone, so for all individuals X. So cut hair is my predicate saying cut hair XY means X cuts the hair of Y. right? So barber cuts the hair of X if and only if X doesn't cut their own hair. Okay, it's a negation of cut hair XX. This is a statement. This, what's inside the brackets is a claim. Its negation is a proposition I'm trying to prove. And this proof naturally lends itself to a proof. The statement naturally lends itself to a proof by contradiction. So I would start off by saying, suppose for the sake of contradiction, the negation of this holds, namely the claim is true. So what is inside the brackets is true. So suppose for the sake of contradiction, there indeed exists a B such that for all X, this equivalence holds. Well, then from there, I'm going to go ahead and derive a contradiction, right? So let's do those manipulations. So if this is the case that, for all X, this holds, this second part holds, then I can in particular consider X to be equal to this B, whatever that B is. So you told me that X is a barber such that for all X something holds. So let me take that X to be the barber itself and substitute that into this expression. Right? So this claim that for all X this holds implies that in particular for B this holds. So what does it now? It says not cut hair BB because that's X is B, if and only if cut hair BB, because the second B comes from the X here, right? And so this is saying the X is a B such that something if and only if the negation of that. And that is false, that evaluates to false. So this is that X is B such that false, and that itself is false, right? So this yields the statement false, which is a contradiction, right? Which is what we mean by a contradiction in this case. So we have proven that whatever we suppose for the sake of contradiction here implies false. So so this what we suppose must be false. So its negation is true. Okay. So that's one example. Here's another example which is a little more. If the other one looked more like a curiosity, here is something which is more useful. So take any two prime numbers p and q. If you took the logarithm of q to the base p, then what you get would be an irrational number. Okay, so I'm not going to define what logarithm and primes are for now. We just assume that we have all those things at our disposal. So this is what we want to prove. Okay, so I'm going to appeal to your high school algebra knowledge to go through this proof. Okay, and I'm going to prove it by contradiction. So suppose, for the sake of contradiction, that indeed this is a rational number, right? That what does it mean for something to be a rational number? There exists, okay. So rather, first I should say, for the so this statement was saying that for every pair of primes PQ, this is irrational. So its negation is that there exists some pair of primes for which the logarithm is rational, right? So that's important. It's saying that there exists a pair of prime numbers for which this logarithm is rational. Now, what does it mean to be rational? Well, it means there exists some positive integers a, b such that the logarithm here is of the form a divided by b. Okay, and I'm skipping over details like these are positive integers and so forth. Okay, so now if there are if a by b is the logarithm of q to the base p, then by the definition of logarithm, that means p to the power a divided by b is equal to q, and you can exponentiate both sides by b, the integer b, and you will get p to the a equals q to the b. Okay. Now, so far so good. Where is a contradiction? So this says here are two distinct prime numbers p and q, such that p to the a and q to the b, both for some numbers which are not both or 0, let's say they're both positive integers, p to the a is equal to q to the b. So there is some number that can be written both as p to the a and as q to the b. So that is two distinct prime factorizations of the same integer. Remember, p and q are prime numbers, so you're basically writing this is a prime factorization of the number as the same prime number multiplied a times together, and here another prime number multiplied b times together. Okay, so these are two distinct prime factorization. Now we don't have any contradiction yet, but we can bring in one more theorem that's already proven or known, and that's a fundamental theorem for arithmetic, which we will see later, which says that every integer has a unique prime factorization. So it cannot be the case that you have two prime factorizations. So combined with this fundamental theorem of arithmetic, this statement gives you a contradiction. So as you see, this proof by contradiction is quite useful when often when you're asked to prove something doesn't exist. Now for the sake of contradiction, you get to assume that it does exist. So in this case, that it is rational, there exists a b, and then go ahead and work with it and obtain a contradiction. So if you are kind of stuck, you don't know how to start a proof, you might want to look at looking at proof by contradiction, so that you get to assume that it's the opposite, that in this case there exists something, and then you have something concrete to work with. Here's another kind of recurring theme in proofs that you might come across, which is you're required to prove some proposition P, but instead you dream up some other proposition R and show that R implies P, and then separately work on proving R. Okay, so if you prove both R and R implies P, then that implies P. I mean, that's equivalent to R and P, which in turn implies P. But why would you want to do this? And the reason is that this first step you did here, showing R implies P, in some sense left you with the task of showing R. Okay, so you change the problem which was originally to prove P to a different problem which is to show R, thanks to the work you did in proving R implies P. Okay, so this is called a reduction. Instead of so you have reduced the task of proving P to the task of proving R once you have done the proof that R implies P. Okay, and this is actually a very common way in which proofs get done over a long period of time, with different mathematicians proving carrying out different reductions one after the other. So somebody, instead of proving R, they just don't know how to prove, sorry, instead of proving this P, they would conjecture something another proposition R and say, okay, if R holds, here is my proof for P. So now somebody else could come along and try to prove the conjecture R. They may not be able to do that. They will come with another conjecture R prime, such that and show that if R prime holds, then R holds, until hopefully someday somebody will come and start from the axioms and show that R prime actually holds, and then all these things put together is a full proof of the original proposition P. Okay. Now, when somebody proves R implies P, they're not really saying, they're not really conjecturing that R is true. They're only saying that if R is true, P is true. They leave open the possibility that in future somebody might actually say P is not true, in which case this yields a proof for not R, because remember, R implies P is the same as not P implies not R, and if you prove R, you will get P, but from the other side, if you prove not P, you will get not R. So you could use this one proposition for either case, depending on how things turn out in future, right? So, and this is a very common theme in theoretical computer science, especially where we have a lot of proofs where we don't really know whether to believe, P or not P, but nevertheless we'll give this connection that R implies P, and in future this could either be used as a way to prove P by proving R, or as a way to prove not R by proving not P.